Okay, welcome everyone. Welcome to this final talk of our cartoon conference for this year. It's my pleasure to introduce Tasho Kaletha, who will talk about a twisted U construction and Harish-Chandra characters.
Well, thank you very much for the introduction, and also thank you for the invitation to speak at this conference. I want to talk today about a modification of a well-known construction due to JKU of supercuspidal representations of reductive p-adic groups, and various applications of this modification that all revolve around the Harish-Chandra characters of the resulting representations. And before I discuss the construction and its modification, I want to introduce what is the subtitle of the talk. I'm calling it A Tale of Three Sign Characters, and I want to introduce these, at least in notation, because these were the objects that pointed to us that the U construction will have to be modified. And the first one I'll be calling epsilon sharp, and the next one I'll be calling epsilon flat, and the third one I'll be calling epsilon f. And I'm introducing them in notation now so that as I progress with my talk, you'll be able to spot when they arise and how they come up. And then eventually I'm going to explain to you what they actually are. I'll write down formulas for them. But for now, all I want to say is that all of these are characters, so group homomorphisms defined on a maximal torus, T, in a connected reductive group G, defined over a local non-Archimedean field. And when I write T and G, I'm going to mean the rational points, so the F points, where F is the non-Archimedean local field, but I'll save notation by not writing F. And so these are group homomorphisms to the multiplicative group of plus minus 1. And the epsilon sharp arises from Brouhat-Titz theory. So it in particular will depend on a point X in the building of G. The epsilon flat arises from Galois theory and actually from considerations of the Langland's dual group of G. And the epsilon f arises from Lie theory, again on the side of G. So let me remind you a little bit of U's construction of supercuspidal representations. I have the benefit of having had multiple talks before me discuss various things, and one of the talks of Adele discussed U's construction. So if you went to that talk, it will be somewhat familiar to you. So U's construction from a paper of JKU from 2001 is a way to produce supercuspidal irreducible representations of the reductive group G. And it uses for this a so-called U datum. And what a U datum is, first there is this tower of connected reductive subgroups of our group G. Each of those is defined over the ground field F, and it is a Levy component of a parabolic subgroup, but the parabolic subgroup is only defined over an extension field. So this is what are called twisted Levy subgroups. And then there is a representation pi minus 1. This is a depth 0 supercuspidal representation of the smallest group in the tower, the group G0. And then there is a sequence of characters, phi 0 to phi d. So each phi I is simply a linear character, a group homomorphism, on the corresponding group GI, valid in the multiplicative group of the complex numbers. And there are a few conditions that I don't want to spell out, which these data are supposed to satisfy. But out of them, U's construction produces an irreducible supercuspidal representation. In fact, not just a single one, but one for every member in this tower. Usually we're interested only in the group G, which is the last member of the tower. And so the resulting representation will be pi sub d, but in fact we get a representation for every member in the tower. And I'm not going to say anything about how the construction works. I'll be happy to discuss this later privately if people are interested. All I'm going to say for now is that what the construction actually produces is a compact, it's a subgroup K sub I, an open subgroup of GI, compact modulo center, as well as an irreducible representation rho I, which is then compactly induced to produce the representation pi I. And it is a fair question to ask, how many representations does one get from this construction? Does one get them all? This is the question of exhaustion. When is U's construction exhaustive? And the first result in this direction was given by Julie Kim from 2007, who said that we get all supercuspidal representations when the base field has characteristic 0 and the residual characteristic P is large enough with respect to G, where large enough can mean very large. And this result was refined by Finson in 2018 to give a precise bound on P. It is enough for P not to divide the order of the Weyl group. And moreover, one does not have to assume that the characteristic of F is 0. Could be also a positive characteristic. And the next result that will be important for us is a formula for the Harish-Chandra character. This was due to Adler and Spice from 2008. And this formula, so I think in Gilin's talk, there was some discussion of the Harish-Chandra character distribution, and that it's represented by a function. And so this formula gives a formula for the values of this function, evaluated at a regular semi-simple element in the group. And Adler and Spice say, if we want to compute the character, which I've denoted by theta here, we first have to write the element gamma, the regular semi-simple element, as a product of what people refer to as a head and a tail. So the head is the part of this regular semi-simple element whose root values are sufficiently shallow in terms of Moy-Prasad filtration theory. And the tail is the other part where the root values are deep. And what the formula says is, look at all possible ways to conjugate the head so that it lands in the next smaller group in the tower, GD-1. And for each way to conjugate the head, there will be some contribution from roots of unity. And those roots of unity will actually be of importance to us. This will be the main focus. And then there's a contribution from the character of the representation of the next smaller group. Remember, there is a representation for each member of the tower. So we're looking here at D-1. This is where the head goes, and the tail goes in this mu hat, which is going to be a Fourier transform of an orbital integral. Now, this is the qualitative shape of the formula. But there is one key technical assumption that's quite stringent, under which the formula is valid. And this technical assumption is that this next to last group in the tower is supposed to be compact modulo center. And this is a very, very strict assumption, and that will play a role in what is to come next. Let's look at the simplest cases in use construction, the situations where the tower is as simple as possible. These are the so-called Toro cases. So the Toro case is when the U tower only has two terms, the group G that we're interested in, and a subgroup which is already a maximal torus. And there is no pi-1, and there is a single character in the whole list of characters. We could add a phi-1, but that doesn't really change things. That's just for cosmetics. The resulting representations are called Toro. And here is a little bit of what people have been doing with Toro representations. So if you consider the unramified situation where the torus T splits over an unramified extension, so in particular G must split over an unramified extension, then Mark Reeder in a paper from 2000 organized the resulting representations into L packets. This notion came up in Alex's talk today. So these will be L packets, finite sets of supercuspidal representations. Reeder gave a construction of them, and then there was a question of stability, which also arose in Alex's talk. In this particular situation, the question is, if you take the sum of the Harish-Chandra characters of all members in the L packet, is the resulting function invariant under stable conjugacy, which is conjugacy over the algebraic closure. And this was studied by De Backer and Spice in a paper published in 2018, although the work was done a couple of years earlier. And they found that this actually wasn't the case. These L packets failed a very important conjectural property, stability, and De Backer and Spice isolated the obstruction to these L packets satisfying stability. And that abstraction was the first of the three sign characters, epsilon sharp, that I introduced in the beginning. So The next case, or the polar opposite case on the Toro spectrum, will be when you take a ramified torus, and then the phi 0 is a character of minimal depth in a certain sense. So those were the epipelagic representations identified by Reader and Yu. And I studied those a few years later and organized those into L packets, and then also studied stability. And what I found was that the naive construction also didn't satisfy stability. I should say that Reader and Yu had also related work on organizing these representations into L packets. There was again an obstruction to stability for these packets, but it was different from the one in the unramified case. It was the character epsilon f, one of the three characters I introduced earlier. And then one can look at a general Toro representation. So the torus is general, phi 0 is general as the axioms of U datum allow. And then those I also organized into L packets and studied stability, and saw that the naive construction you could make, obviously you couldn't expect that it satisfies stability given that there were special cases treated earlier that didn't, but the question was what would be the obstruction, how bad could it get? And interestingly enough, it got only as bad as it had to be, namely the obstruction was just the product of the two obstructions that had been seen earlier, nothing new arose. So how does one deal with this obstruction when already de Backer and Spice gave us a way to do it? We just sweep the obstruction under the rug. What does that mean? Well, there is this character phi 0 waiting here. Why don't we just reparameterize everything by multiplying it by the obstruction, absorbing the obstruction into phi 0, then it goes away and we don't have to worry about it. So wonderful, let's do this. Problem solved. So this was the Toro case. The Toro case is a very, very special case of a U tower that is as small as possible. On the opposite end of that is the regular case where we take an essentially arbitrary U tower. The tower of groups can be as long as you want, the characters can be. You only make one assumption, and that assumption is that this pi minus 1, the depth 0 supercuspidal representation, so let me remind you that was this part of the U tower, supercuspidal representation on G0 of depth 0, that we're going to assume is a regular Deligne-Lustig representation, which means Moyen-Prasad theory explains that depth 0 supercuspidal representations are related to cuspidal representations over the finite field, and there we have Deligne-Lustig theory. So we assume that pi minus 1 is related in this way to a regular Deligne-Lustig representation, which is in some sense a genericity condition. Most cuspidal representations are of this form. So let's call the resulting output of U's construction regular. And I studied those in the same paper where I studied the general Toro case. And here is what you find out. Since the supercuspidal representation is a regular Deligne-Lustig representation, it corresponds to a pair of a maximal torus and a character, a maximal torus in G0, and a character of this maximal torus. So now we have the entire sequence of characters from the U datum, phi 0, phi 1 to phi d, and we have this character phi minus 1. We can multiply them all together and obtain a character of the torus T, call it theta. And it turns out that the regular supercuspidal representation pi depends only on the G conjugacy class of this torus character pair. And moreover, you can write down a very simple list of axioms characterizing precisely which torus character pairs are involved in this classification. So you get a classification of the regular supercuspidal representations by conjugacy classes of torus character pairs. And what is nice about this is that this is exactly the same classification as in the case of discrete series representations of real reductive groups. The one key difference is that for a real reductive group, there is a unique conjugacy class of elliptic maximal tori. And so usually people drop it from notation and only think about the characters. Whereas for a p-adic group, there is plenty of different conjugacy classes of elliptic maximal tori, and you have to consider them all. The next thing is that you can show that even though the Adler and Spice character formula was valid under a very strict compactness assumption, if you consider very special elements that you're going to feed in it, namely elements of that particular torus T that are themselves shallow, in that situation, you can drop the compactness assumption. And then one can reinterpret the roots of unity in that formula. And here is what one finds. So this is the value for the character of pi at this particular shallow element gamma of the torus T. There is a plus minus in front called the Cotwit sign, which is well understood from the 80s and shows up at various places in harmonic analysis and representation theory. In the p-adic case, it's nothing more than -1 raised to the relative rank of G minus the relative rank of its quasi-split inner form. Particularly, it's 1 if the group is quasi-split. Then there is a root number here of a certain Artin representation that you make up from the character module of the torus T and the character module of another torus T0 that's canonically associated to G. Has nothing to do with the representation. It's simply the minimal Levy in the quasi-split inner form. So the maximally split maximal torus in the quasi-split inner form. Then we have a sum over the Weil group. And we have a term here that I'm going to explain a little later. Let's just leave it at that. We have the theta, and then we see here again our two obstruction characters that we already saw, epsilon sharp and epsilon f. And again, the good thing about this formula is that this is the same formula as for discrete series over the real numbers, except for this obstruction, epsilon f and epsilon sharp. So what can we do with this? Again, we sweep the obstruction under the rug. We make it disappear by absorbing it into the character theta, effectively reparameterizing this correspondence here, this bijection. After we do this, the character formula looks exactly like that for the real discrete series. And what this allows us to do is to obtain the local Langlands correspondence for these representations by mimicking Langlands' original argument over the real numbers. I won't go into any details about how this is done. I'll just give a very impressionistic picture because I want to move on beyond the regular case. Basically, what you do is you start with a supercuspidal parameter, which Alex explained this morning what it means. It means a discrete parameter on the Weil-Deligne group that is actually trivial on the SL2 part of the Weil-Deligne group, so it's only defined on the Weil group. And you impose a regularity condition on it, which a stronger version of it would be that the centralizer of the image of inertia is abelian. And the usual regularity condition is a little more complicated to state, so I won't do that. And once you have this parameter, it naturally leads to a torus. And then what you want to do is you want to use functoriality for that torus. That is, you'd like to fix an embedding of the L group of that torus into the L group of G. There is no canonical such embedding. It has to be chosen. So we make a choice for it. I've called it here chi. And once we make such a choice, now we have our parameter here, and it goes into LG. It actually factors through and becomes a parameter for the torus. So it gives us a character on the torus by the well-established local Langlands correspondence for tori. And then we can write down the following formula. So we can, which looks very much like this formula up there for the character. We use the same roots of unity here in front, the same sum. And then we use the character that we have obtained from the local Langlands correspondence for tori. It depends on chi, but this delta 2 that I left unspecified, this is a root of unity that also as an input needs the same chi. So I would see this as a transfer factor for this functoriality that we're using right now, and it depends on the L embedding. And the dependence of the two pieces here cancels out so that the product of them is something canonically associated to the Langlands parameter. And now this formula looks exactly like this formula, except for the obstruction that we've swept under the rug. And because of that, we can use it to pinpoint a representation. And we do this for every way to embed the torus into the group. And by this, I don't mean the L group of the torus into the L group of G. I mean on the non-dual side, you can embed the torus into the group in various ways. Each time you get a representation, and the resulting collection is the L packet. Okay, so this was where things stood around 2016-17. And the next thing that happened is that the rug that we've been sweeping things under decided to take revenge on us. And this happened in the following form. So Lawrence Spice and I were working on two kind of separate things. He wanted to drop the compactness assumption from his character formula. I was able to do this only for his very special gamma, but he wanted to do it for arbitrary gamma, and the situation there becomes very, very complicated. And what he found while doing so is that there was actually a mistake in JKU's paper. And that was a rather serious mistake. And it was quite unfortunate because in some sense it wasn't JKU's fault, but rather JKU was using a lemma from a paper of Girardin from now 40 years ago. And that lemma was there was a typo in the statement of that lemma. If you looked at the proof of the lemma was correct, but it didn't prove the statement. It proved the formula that was different from the stated formula and differed by a certain sign. So the formula was a formula for the character of the Weil representation, and there was a piece of it missing. And because of that, what happened was that there is an important intertwining result in Yu's paper, and that intertwining result, at least the proof of that, failed because of this typo. So let me go back here. I mentioned to you that Yu's construction produces the supercuspidal representation by a compact induction of a certain finite dimensional representation of a compact open subgroup. Now, if you want to get an irreducible outcome, not only does the thing need to be reducible that you're inducing, namely the rho, but you also need to know that if an element in the group GI intertwines rho, then it actually lies in the inducing group already. Otherwise, the induction is not irreducible, but then it's also not supercuspidal, so the whole thing, the whole construction falls apart. Well, Yu's intertwining proof fails, and that's why his irreducibility proof fails too. And later, Finsen was able to tell us that not only did the intertwining proof fail, but in fact, the intertwining claim is false. She was able to produce a counterexample to the intertwining claim. Nonetheless, the irreducibility claim was true, which was good news for anybody who had used Yu's construction for various things. The construction still produced what it claimed to produce by a different argument. For us, however, this was not good enough because, or for Lawrence Spice, I should say, he needed those intertwining results in his character formula computations. And he was able to isolate the abstraction as to why the intertwining result fails. And that abstraction was again, that abstraction was again the same epsilon sharp that was already an abstraction to stability for unramified Toro supercuspidal representations. So Lawrence Spice formulated a hope. He was hoping that this abstraction character would extend from the torus where it is defined on to the stabilizer of the point X in the group G0. Now, this is the first time the point X comes about, so let me just mention, the point X is secretly part of the U datum because the depth zero supercuspidal representation arises by Moy-Prasad theory from a cuspidal representation over the finite field, and there is a point X whose parahoric group you take and you do reduction mod P and use a cuspidal representation there. So the point X is part of the U datum. And what Spice observed is that if this abstraction character would extend to the stabilizer of that point, then one could reparameterize Yu's construction so that, and in this way, restore the intertwining claim. Now, parallel to this, I tried to construct the local lines correspondence for arbitrary supercuspidal parameters that are not regular when the P does not divide the order of the Weil group. And what this meant is because pi minus 1 is no longer regular, we don't associate a torus. It doesn't come from the Lin-Lustig construction from a torus. So instead of passing from a torus to G, we have to pass from G0 to G. G0 is where pi minus 1 is defined. This means that dually we're looking at functoriality not from the L group of a torus, but from the L group of G0. And that change in the functoriality you're thinking of introduces another sign character, and that sign character is this epsilon flat, the final one of the three that I introduced earlier. And independently, I formulated my hope. G, it would be nice if this epsilon flat extended from T to the same stabilizer of the point, because then I could sweep it under the rug again, and things would be nice. And then Lauren and I started talking, and we quickly realized that these hopes are well unfounded, because neither of these characters extends from the torus to G0x. So something else was going on. There was a third sign character, if you remember, epsilon f. Let me just assure you that at least this one does extend, so we weren't too worried about it. We knew how to handle it, at least in an ad hoc way. But we didn't know how to handle the other two. So now that I've motivated for you, hopefully, how these three different sign characters come about, maybe it's time for me to tell you what at least epsilon sharp and epsilon flat are. I'm going to give you the formulas for them. And maybe they may look a little technical if you've never seen them before, so I'm going to spend a few minutes explaining what the different bits of them are. And it's not too important to understand everything. In the end, they're actually very elementary. There's nothing complicated about them. What's important is to pay attention to the qualitative picture. So here are the formulas. What you'd notice, let's start just by zooming out. What you'd notice is that optically, they look very similar. You have two formulas that look very, very similar. So what do you have? You have two products in both cases. And the factors in the products are exactly the same. Moreover, you have index sets, and the top parts of the index sets are also exactly the same in both cases. So if you think about this, epsilon sharp was a character coming from Brouhat-Titz theory on the side of G, and it has to do with the Weil representation. Epsilon flat is a character coming from Galois theory from the side of G hat. And it is quite astounding that they actually are going to have almost identical shape, even though they come from completely different sources. And then you might think, well, if I see obstructions from two very different places that seem to come together and have the same shape, they better be the same obstruction. I must be looking at the same obstruction from two different sides. But that's actually also not true, because if you look at the remaining part of the index set, you'll see that this one depends on Brouhat-Titz theory on the point X, that's part of the U datum, whereas this one only depends on Galois theory. So, it's not too important to understand exactly what these formulas say. Let me say a few words so that you get a rough idea. So the products are over roots. You base change to the algebraic closure or separable closure, and you look at the absolute root system of the maximal torus T in the group G. And you look at how the Galois group acts on this root system, because everything is defined over the ground field. There is a Galois action on the root system. And we can classify a root as being asymmetric, which means that the negative root is not contained in the Galois orbit, or symmetric, which means that the negative root is contained in the Galois orbit. And then a symmetric root can be unramified, which means that even though the negative root is contained in the Galois orbit, it's not contained in the inertial orbit. So this is what these indexing sets are. We're looking at Galois orbits of symmetric unramified roots, or pairs of Galois orbit and its negative of asymmetric roots. Here, sigma is just Galois together with plus minus 1. So we're looking at pairs of an orbit and the negative orbit. And when we have a root, we can evaluate the element of the torus on it. We get some element in the algebraic closure. But because it's a compact element, it actually lives in, it's an integral element that lives in a finite extension. We can reduce mod p, and we have an element in the multiplicative group of a finite field. We're assuming that the residual characteristic is odd, so this is a cyclic group of even order. It has a canonical quadratic character. That's what this sign is. Similar thing here, except that the way things are set up, our element lands in a certain subgroup that's a kernel of a norm. So that's as much as I want to say about this. And then the parts where these two characters differ are, in this case, the point in the Brouhat-Titz building gives us a filtration of the root group corresponding to the root alpha. And this filtration has jumps. These are the real numbers where the filtration changes. This is what this set measures. And we're wondering whether the depth of the representation divided by 2 is a jump of the filtration. Whereas down here, we're doing something completely different. What we're doing here is we are restricting the root to the center of G0, which is some smaller torus. And then we're asking that this restriction be symmetric and ramified, even though the original root was asymmetric or possibly symmetric and unramified. We want its restriction to be symmetric ramified, and we want a certain ramification degree to be odd. I can say more later for whoever is interested. So our hope was, I'll remind you, that the product of these two sign characters would extend from the torus where it is defined to the stabilizer of the point X in the group G0. And we did a few examples, and something very interesting happened, because as you move the point in the building, the product of these characters changes, because the first one of them changes. And so it becomes more or less difficult for this character to be extended to a bigger group. At the same time, of course, the parahoric changes as well, and it makes more or less demands on a character to be extended to it. And the two changes were completely parallel in each case. So something really interesting was going on. But the other thing that was interesting is that we didn't just have one fixed torus from which we were going to extend these characters to the parahoric. We wanted this to happen for every possible torus that sees the parahoric. And if you see how these characters are defined, they depend on the way the Galois group acts on the root system. And if you change the torus, this will radically change the way the Galois group acts on the root system, or in other words, the orbit structure. And yet we were saying that even though this is the case, there is a universal character on the parahoric that restricts to all these different tori to give us these different sign characters. And this is in fact our main technical result, that this is the case. So the result is that there exists a canonical sign character on the stabilizer of the point X in G0, such that for every maximal torus, that's a typo, this should be in G0. Every maximal torus in G0 whose building contains X, the restriction of this sign character to that torus gives the corresponding epsilon sharp and epsilon flat for that torus. So this is very nice. And even though, as you saw, these formulas were very elementary, we found it was rather difficult for us to find this sign character. And you'll see in the next slide why. The main point is that these, did you see my next slide? Which slide are you guys looking at? Because on my computer, I think the previous slide is frozen.
We're still looking at the formulas.
Uh-oh. Let me see why this is. Okay, just a moment. Okay, do you see the next slide now?
Yes, main technical results.
Okay, wonderful. I'm not sure.
You might want to move your mouse to the side as well.
Like this?
Yeah, perfect.
Okay, thank you. So the main technical result is that there does exist a canonical sign character on the stabilizer of X in G0, whose restriction to any maximal torus whose building contains X is the product of these two sign characters, epsilon sharp and epsilon flat. And initially, we tried to work with the explicit formulas that I just gave you and made some partial progress, but we're not able to get the complete result. we're only able to get it after we completely switch gears, and what we did instead is perform certain very natural constructions that were completely unrelated to the formulas we had, and we're just hoping that they would give us what we wanted. And so that's why it took us a lot of time to get this, even though it's such an elementary result in the end. And we were very happy to find that we got these two characters, except we also got the third one. As we were computing, as we were unwinding our constructions and we were getting out the first characters, we got very excited, but then the third one popped up. We got even more excited because even though we didn't initially want to get it because we knew how to handle it in an ad hoc way, well, it's much better to be able to handle it in a canonical way. So there it was, just waiting for us. Except we got yet another one. And that one we really didn't expect. We were surprised but not excited. And now I know what some of you may be thinking. You may be wondering whether this new one that we didn't expect, maybe it is just the product of the first three, and then this canonical thing is nothing, it's just one. Well, I was sure this is not the case. The auxiliary character that we found is actually a very benign thing that easily extends to G0x. So this theorem does give us the extendability result that we wanted, but as you'll see in a couple of slides, actually this auxiliary character fits perfectly into place. We just didn't anticipate it from the beginning. But we were at that point happy that at least the epsilon f came for free, even if we didn't initially want it there. So now let me tell you a little bit about how this epsilon was defined before I move to the applications of this technical result. So the construction of this canonical character epsilon, it has three pieces. The three pieces have nothing to do with the three pieces that it ends up giving us. It's a completely different thing. Most of it takes place over the finite field. So here is roughly the construction. The first piece is to take an affine algebraic group over any field whatsoever of odd characteristic. You have to allow that this group is disconnected and its connected component is reductive. For us, K will be a finite field, the residue field. And you take an invariant non-degenerate symmetric bilinear form on the Lie algebra. And then the adjoint action gives you a map from the rational points of H to the rational points of the orthogonal group for that symmetric bilinear form. And on the orthogonal group, you have this wonderful homomorphism called the spinor norm that goes into the square classes of the ground field. And the spinor norm is, it can be characterized as follows. Anytime you have an anisotropic vector in the quadratic space, you look at the reflection, and the spinor norm sends it to the value of the quadratic form at that vector. So that's, you can take this as the definition if you want. It's absolutely not obvious from this definition that this is a group homomorphism, but it is. So that's the first piece. As you can see, it really has nothing to do with the formulas that I showed you earlier. The second piece is again over the finite field. You take again an affine algebraic group over K, you allow it to be disconnected. It doesn't even matter if the connected component is reductive, although this is the main case of interest. And then you look at the multiplication by 2 map on its group of algebraic characters. And you can think of this as a complex placed in degrees 0 and 1. And you can realize this complex is the internal hom from the complex that is H just placed in degree 0 to the complex of GM to itself via the squaring map. And then you look at the Galois hypercohomology in degree 1 of this complex. And there is a very elementary map going from that to the homomorphisms from the rational points of H to the Galois hypercohomology group of the complex of just GM to itself by the squaring map. And that complex here is very simple. It's just quasi-isomorphic to mu2, to the kernel of this map. So you get homomorphisms into H1 of mu2, but that's just, again, the square classes. So these two pieces, the way they're applied is you take the Bruhatid's group scheme for the group G0 in the point X. It usually has disconnected fiber, and that's very important for us. And you pass to the reductive quotient, and you apply these two pieces there. There is a canonical non-degenerate symmetric bilinear form, and there is also a canonical element in the hypercohomology of this complex. I can describe them in chat later so that, whoever is interested. And then there is a third piece that's just an explicit formula using Bruhatit's theory, so I won't spend time discussing it too much. But those three pieces together, when you multiply them, it turns out after some computation that you recover exactly the three obstruction characters and the auxiliary character that you didn't want to see. So let me now move to the rewards that we get from this. So the first reward is the one that we were hoping for, a twisted U construction. You can take JKU's construction that, I'll remind you, takes this datum here and produces the representation pi by compactly reducing a representation rho. And what you can do now is you can just twist the representation rho by this sign character before compact induction. So this gives a modification of U's construction, and the reward you get from that is that the intertwining claim that used to be false is now true. Now, this may be of independent interest for people applying U's construction. For us, it was of interest because it allows Lawrence Spice's computations to proceed. And Lauren tells me that he can prove the following theorem, which he is now in the process of writing up. I'm going to make the assumption that pi minus 1, the depth 0 piece in U datum, is a Deligne-Lustig induction. I'm not assuming that it's regular Deligne-Lustig. It can be any virtual Deligne-Lustig character. And I'm only assuming this for convenience. Lawrence Spice's formula doesn't need this, but in our later applications that I'm going to discuss, this is the case that we use. And it makes stating the formula easier. So in that situation, this is what Lawrence Spice says the character formula looks like. Again, you're going to break the element gamma into a head and a tail, only now you're breaking it at depth 0 rather than the depth of the representation. Again, you look at the different ways in which you can conjugate the head into the torus T. You have the same roots of unity you had before, but you also have the twisting character here. And then the rest is as before, the character theta, and then the Fourier transform of the orbital integral. What about the roots of unity? Well, remember that this twisting character was the product of these four, the three obstructions and the auxiliary character. Well, the three obstructions, they were also present in these roots of unity here. So they now cancel out. This is why it's good to twist U's construction. What about the auxiliary character? Well, it turns out after thinking a little bit about it for a while that it had to have been there. It just, that's how cosmic justice works. So what happens was, if you remember, there was this delta 2 term a little bit earlier. So let me, here it is. So this was the way the character formula looked before. And there was a delta 2 term in it. And that delta 2 term was a facilitator in Langland's functoriality between LT and LG. It depended on the L embedding. Now, we decided we were going to do functoriality not from T to G, but from G0 to G, because we're dealing now with non-regular representations. And because of, but even though, almost got the right slide. Even though we were now looking at functoriality from G0 to G, we were still using the traditional Langland-Shellstad's way to compute delta 2 in terms of the data of the L embedding restricted to the torus T. And while this is reasonable if we are computing characters, because there is a natural T, if you look purely from the point of view of functoriality, this is not the most natural thing to do, because from that point of view, the torus T is external. There is something more natural to do if you decide, if you allow yourself to use a torus that is not maximal, because then there is a canonical choice, namely the center of G0. It's there and it's only dependent on G0. And guess what happens when you multiply this delta 2 by the auxiliary character? You get the same delta 2, but now only with the data dependent on the center of G0, which is a much more canonical thing. So in other words, even though we did not expect the auxiliary character, it just fell into place perfectly and told us the only reason it appeared auxiliary was because our earlier construction were not as natural as they could have been. So from that point of view, we can now state the character formula in the following form. We have these terms that we want to see. We have a canonical delta 2 dependent only on G0, that's this delta 2. And then we have the character theta and the Fourier transform of the orbital integral. So in other words, that's a completely clean character formula that matches perfectly with the case of representations, discrete series representations of real groups, and you don't have to reparameterize or sweep anything under the rug. Things just line up perfectly. And what this allows us to do finally now is realize functoriality from G0 to G, and in particular transfer a local Leibniz correspondence from G0 to G. That is, if we understand local Leibniz correspondence for depth 0 supercuspidal parameters, we can apply it to G0, we can use functoriality from G0 to G, and we get local Leibniz correspondence for all supercuspidal parameters. But the thing is, we actually do understand local Leibniz correspondence for depth 0 supercuspidal parameters. That's something that initially I was thinking of discussing, but I think it may not be, there may not be enough time to do this. So I'm happy to talk about it in the chat. I've given some talks about it previously. So, but the upshot for us here is that we now have an explicit local Leibniz correspondence for all supercuspidal parameters. And including the internal structure of L packets, which is something that in Alex's talk came up as BIJ, the bijection between the packet and the irreducible representations of the centralizer of the parameter. The next application we get is character identities. So let me remind you, Alex talked about them briefly. Let me remind you of the conjectural setup very quickly. So we consider the centralizer of the image of the parameter, and the internal structure that I just mentioned, it takes the form of a bijection between the elements in the packet and the irreducible representations of the centralizer. There are various qualifiers here to make this completely precise, which I don't want to spend time discussing. So maybe you want to put quotation marks around this bijection, but it can be made precise with appropriate additional symbols. If you have a semi-simple element in the centralizer, what you can do using this bijection is you can form a virtual linear combination of the Harish-Chandra characters by taking as a weight in front of each Harish-Chandra character the value at S of the corresponding character of the representation on this side. And then I would like to put the Kottwitz sign in front just for normalization purposes. So this is one thing you get from an element in the centralizer, this virtual character on G. You also get an endoscopic group whose dual group is just the centralizer of this S in G hat. And the character identities are the following identity. You have a virtual character on G, and you have another one on H simply because the parameter phi factors through H the way things are set up. And you say that those two virtual characters have to be the same in the sense that if you evaluate one at F, then the other one is evaluated at the so-called transfer of F. I don't want to say any more details about this, but the application we get from the previous applications, if you like, is that if you assume that P is sufficiently large so that you can use the exponential map, then if you have a regular supercuspidal parameter, then these character identities do hold. What happens if you have a non-regular supercuspidal parameter, a general supercuspidal parameter? Well, then as far as we understand it now, here is what happens. The centralizer sits in an exact sequence where there is a piece coming from the dual torus and a piece coming from the Weyl group. In the case of a regular parameter, the piece coming from the Weyl group is not there, and this map is an isomorphism. And what we can show for now is that if the endoscopic element S is in this subgroup here, then again we get the character identities. Again, for any supercuspidal parameter. And if the endoscopic element S does not lie in this subgroup, so it has a trivial image in this Weyl group, then something more complicated happens, and it happens already for depth 0 parameters. And this is work in progress now, but we don't have results yet to report on. So that's something that still needs to be worked out. So I think I'll stop here.
Thank you very much. I think the clapping is happening in the chat again. We give them a moment to finish clapping, and then we look for questions in the Q&A or by raising your hand. Okay, Tasho, there's a question from David Wogan. He asked, does the term supercuspidal parameters exclude those for which just a part of the packet is supercuspidal?
Yes, it does exclude those. Those necessarily have to have a non-trivial contribution from SL2C, the part of the Veil-Delin group that's in addition to the Veil group. So the supercuspidal parameters correspond precisely to packets that are completely comprised of supercuspidal representations.
And there's a second anonymous question. Is there a comparison of the local Langlands correspondence with Winslow-Falk's global parameterization?
No, not at the moment. This is something that is on my mind, but I don't have anything to say about it yet. Okay, let me see. Are there any further questions? Feel free to also raise your hand in case you're typing. Okay, I don't see any raised hands or more Q&As at the moment. So we will have a big Zoom room afterwards where Tasho will have a small Zoom room. So feel free to come and ask more questions there as well. So let's thank Tasho again. Thanks. Thank you.